We start with our first talk by Konstantinos Kaparis, and he will tell something about the casting planes for first level RLT relaxation of mixed 0-1 program.
Hello there. I'm Konstantinos Kaparis from Lancaster University. This is some joint work with Professor Adam Ledford and Franklin Fomeny from Lancaster University as well. So I'm going to discuss some new cutting planes for first level RLT relaxations, and here is the outline of my presentation. I'll give a brief introduction with regards to the RLT hierarchy, and then literature review. I will describe the cutting planes, the separation algorithm that we have for them, and also some computational results applied to the quadratic knapsack problem. We finally reach some concluding remarks. So the RLT has been proposed by Sir Elliot Adams. It has been used to construct LP relaxations, and these LP relaxations, this hierarchy of LP relaxations, it is known that it will span the whole space from the continuous relaxation up to the complete convex hull description of the original problem. So each level, it's actually an outer polyhedral outer approximation of the previous level, and as we traverse the hierarchy, the bound gets stronger and stronger. However, the size of the problem gets substantially large as we traverse the hierarchy. And that's why, in most practical cases, people resort to the first level RLT only, which proves in most cases to provide a very strong bound anyway. So in our work, we have as, let's say, playground, this first level RLT relaxation. And you can think of our approach as a way to harness some of the strength of the second level without using the variables, though, of the second level. It's something like a projection approach. So the roots of the RLT hierarchy can be traced back to the seminal paper of Sir Elliot Adams in 1986. In this paper, there's no any discussion about the hierarchy, the RLT hierarchy, but it's maybe the first application of the first level RLT. So Sir Elliot Adams used the first level RLT in order to construct tight linearizations of 0-1 QPs of the following form. In this case, we assume without loss of generality that Q is symmetric, and also denote by V the set of indexes of our variables, and T all the pairs of all the sets of pairs of variables indexes in set V. Right. So using now this using this framework now, we can move into a higher dimensional space by introducing Yij variables, taking the value 1 if and only if xi and xj is also 1. In this way, we can provide the following reformulation. That's a very well-known result. So we use the variables y that we just introduced and 3 times cardinality linearization constraints. This formulation basically was already known by Fortet in 1959. It has been used by others like Glover and Woolsey later on. Usually, if you take the LP relaxation of this formulation, the bound is very weak. What Adams and Sir Elliot introduced in that paper back to 1986 was a set of polynomial constraints that can be added to this original problem in order to strengthen the bound. So, assuming now that we have a linear system, we multiply every constraint of our original system with the one variable or the complement of one of the same variable. So we can obtain in this way 2 times m times n constraints. Of course, this form makes use of the classic results that in the binary case, x squared is equal to x. Later on, in 1990, Sir Elliot Adams realized that this approach can be further generalized And in that way, they've introduced their hierarchy. So they know that they can introduce for each level products up to k+1 variable, and constraints that represent products of this k+1. They can introduce polynomials of k+1 degree just by taking k+1 constraints and multiplying them together. So this technique is a technique that they call the reformulation linearization technique. Since then, there have been some developments. So Lovaas and Schrijver show that this approach can be generalized to for zero-arm problems with convex constraints. Furthermore, Adams and Cerali produce a series of papers generalizing this approach furthermore. So there is paper for the generalization to the mixed 0-1 case or to the discrete, to the general discrete case. Finally, there are various papers, various works concerning particular polytopes that are related to some 0-1 QPs, like the cat polytope and the work of Padberg. So as I mentioned before, the main problem, as we traverse the hierarchy, the main problem of using higher level hierarchies from the RLT is the fact that the number of variables grows substantially. So what we do is to concentrate on the first level RLT relaxation. And in some sense, our approach is very similar to the RLT. We still have the reformulation technique. We still try, as in the normal RLT approach, to formulate cubic terms. So we multiply triples of constraints, including the bound constraints, to form cubic terms. However, in the second level, in the linearization phase, let's say, we don't introduce variables that represent those triples. We try to substitute those variables in an optimal way using some linear terms. So that's the classic, let's say, step for getting the second level RLT relaxation. We just assume some linear inequalities. We take 3 of them, and we just multiplying them together. Again, I highlight that this includes the bound constraints. So now the key lemma for our approach is the following. As I said, we can still use the x and y variables that represent the first level, that are present in the first level RLT relaxation, but we want to get rid of all the cubic terms. So the way to do that is to use the following lemma, which bounds the values of our cubic terms. So we know that we have an upper bound for our cubic terms, which is given by the minimum of all those terms. And at the same time, we have a lower bound given by the maximum of those terms. And it's not very difficult to detect this form. For example, you can take the non-negativity of the expression which multiplies xi, xj, and 1 minus xk in order to derive yij. And in the same way, we can derive yik and yjk. While if you take the non-negativity, which is implied by the complement of this product, you derive this term. Similarly, by taking products of one variable and 2 complements, you can derive the 3 terms here, while the 0 is trivial. So the product of xi, xj, and xk is always greater or equal to 0. So this is actually the main tool. We have what we want in order to project from the second level to the first level. Right. So we have a valid cubic inequality now after multiplying 3 together. And we know that we can still use the y variables, but we can replace any term of the cubic term with any of the following 4 terms if the coefficient is positive. And that will still give a valid inequality. On the other hand, if we have a negative coefficient, we can substitute every cubic term with one of the falling terms and still have a valid inequality. We make the cut weaker still, but this is still valid for the first level RLT. Observe also that in this way, one from a single cubic inequality is able to derive an exponential number of valid inequalities for the first level RLT. So we consider now a special case. We call them ST inequalities. And by saying a special case, I mean that I multiply one of the inequalities in our system with, you can view that either as the variables or, let's say, the non-negativity constraints of xs and xt. So that's, again, a multiplication of 3 constraints. And I want this to be greater or equal to 0. So in the binary case, trivially, this holds. So we can rewrite our equation in the following form. Or inequality in the following form, excuse me. So now we need to substitute the xi, xs, and xt. And we have the previous lemma, as I mentioned. We denote, we introduce some further notation here, and we denote by s plus and s minus the variables, the indexes of variables with positive coefficients and negative coefficients. Now, by using our lemma, which I again write over here, we are able to get the following form of the ST inequalities. What we are doing actually here is that we partition our set V to 4 different sets. And these sets are somehow linked to which of the weakenings we apply based on our lemma. For the following inequality, let's say, and given some S and T, we can say that which of the weakening we are going to apply depends on the variable I. So, for example, we might say that in case we can have xist being substituted with yis plus yst minus xs in case this variable is in set S plus. Okay, so we just label, let's say, the substitutions that we are doing. So these 4 cases then correspond to set S plus, T plus, W plus, and R plus. And similarly, the upper bounds correspond to S minus, T minus, W minus, and R minus. So by taking that and substituting in the following inequality, we derive this form. This is the form of what we call the ST inequality. It's not difficult to see then that one can derive some further forms of such inequalities called mixed or reverse, where we now multiply here with the complement to one of the variables and the original variable t, or both complements of xs and xt, and one linear inequality. These inequalities can be strengthened even more. I won't give the full details, but what we are doing is that we take all the different values, the combinations of different values that xs, xt, and yst can take. In that way, we are able to bound the left-hand side of the inequality, and then we can strengthen its right-hand side using these bounds. Also, the method can be applied to problems having a mixture of linear quadratic constraints, which can be even non-convex, the quadratic constraints, or non-linear constraints, as long as they are convex. This is following the argument of Lovaas and Scriver back to 1991. Obviously, all three families of ST inequalities are exponentially large. So we need to think of separation. Surprisingly, and that was a very good result for us, they can all be separated in linear time, in polynomial time. So we can separate them in the case where the constraints are linear in n cubed times m. And it's not very difficult to see why. You have m ways to choose a linear inequality, and there are n squared ways to choose your s and t. So the s and t can be, you can choose them in n squared time, and then in linear time you can check all your i's, and you can make a decision of where you're going to place each node in set S, T, W, R. And this decision is going to be based on the largest value of these falling four terms, which gives you a lower bound for the cubic term, or in the case that the coefficient is negative, in the largest value of these four terms. So you try to maximize the violation that you get through this substitution. Of course, separation for mixed or inverse and ST inequalities can be derived in the same fashion. We saw also in the paper that the separation for the strengthened version has the same running time. It's not difficult to see that in the case that we multiply one variable with pairs of constraints, the running time is going to be n cubed times m squared, because we have two ways to take the couple of constraints. And in the case that we multiply three linear inequalities together, then the running time goes up to n cubed times m cubed. We can also consider the case of a convex. We can also consider the case where there is a convex constraint, and we have polynomial time separation for that. In that case, all that we need, based on the Lovas and Scribers paper back to 1991, is to get three inequalities which are valid for set C. And you can use those inequalities in order to derive outcuts. We have some preliminary results using the quadratic knapsack problem. I will have to say that in some sense these results underestimate the performance of our model, because I know now that my algorithm, my implementation misses some cuts. So they can only be better than what you're going to see. For this set, we just take 5 instances, each of different combination of size and density of the quadratic matrix in our objective function. We separate all three families of strong inequalities for now. And we compare the resulting bounds against the benchmark bounds given by the first level RLT relaxation. So what we have here is the density, the number of variables in our original problem. This is the bound of the RLT relaxation. This is the gap from the optimum, the percentage gap from the optimum, which is very good. I mean, in that case, RLT performs really well. And this is what is the bound when we add our strong ST inequalities in those RLTs. This is the improvement that we get when we add the percentage improvement, the ST inequalities for all different cases. You can see that the improvement is quite substantial, and what is missing here, and someone definitely will complain, is the running time. I don't know why I forgot to include that, but I can tell that there is definitely a tailing off phase in our approach. But the major improvement, it happens at the very first few steps of the running time. I can show you the running times, I mean, if you are interested, or even graphs that show how this bound is improved. The major problem here, again, as usual in this case, is the LP solver. So obviously, as we add more and more cards, it's not the separation that takes place, that takes time. It's actually resolving the LP that takes time. And yep, the next table with the same results. You can see that for sparser instances, those ST cards become more important in terms of the additional percentage of gap closed. Right. So we've presented some general procedure to generate general cutting planes for the first level RLT. In the case where all the constraints are linear or quadratic, we have polynomial time separation for them. For the case of converged constraints, we can show that we can provide separation routines. We have polynomial time only for the strengthened ST inequalities. I highlight that this is a special case because in the case of ST inequalities, we multiply two bound constraints with one constraint in our linear system. So if we multiply two constraints of the form alpha transpose x minus beta, then this result doesn't hold anymore. And the computational results, we think up to now, they're rather encouraging. Certainly, we might need to use different test problems, like the quadratic assignment problem, but this is still under development. Thank you very much.
And when I look at those sort of approaches like Sherrod, Adams, and so on, actually, I would like to know how to understand these ideas geometrically. Mm-hmm. Because there are those, I don't know, for just the linear case, there are all those extended formulations. And this approach is also sort of extended formulation. So, can one visualize this somehow?
Personally, I can't tell that I have, a clear visualization of the whole process. I mean, I see what you mean, but
because I mean, for example, if you add variables and you add constraints, you can ask the same questions as for extended formulations. If you have so and so many constraints which you can add, how much you can improve your approximation?
That's a good comment. That's a good question, but I don't have any answer, I'm afraid.
I see.
If it's not the case, let's thank the speaker again.